Um, Hello guys, welcome to part two of my video. Uh, the in the part one we discussed. I did categorical plots, I did statistical plots, I did relational plots, right? Alright, so we are going to continue by doing. Yeah, I'm going to perform fitting. I'm going to do a polynomial fit. Also, from the question it says do a polynomial fit, then we have to do get the confidence interval and the error bar, and we are going to do we're going to make a prediction for some random points. We are going to make some random points and make a prediction line for them. All right, so I'll just get right into it. So yeah, I'm going to write our function polynomial fitting, right? Fitting, and since I'm making a prediction, so I'm going to just say prediction. But I'm just going to display the polynomial fit before I make the uh, prediction of the points, before I make the error bar and show the confidence interval. Right, so polynomial prediction. The most common type of curve fitting is linear regression, right? Where we find the line that best describes the relationship of a variable to another variable, and then we use that line for the prediction. With your string, here I'm going to do polynomial. The polynomial fits that the relationship, yeah. So I'm going to find the two variables to do a polynomial fit on, that the x and y variables, right? Right, so I'll probably use the total actual production here, and the total actual production and hydro generation. So I can do the either the actual or the estimated, but I'm going to use the action. I'm going to use the actual though. So I'm going to do the total actual production and the hydro generation actual in MU. Total actual production and hydro in MU. Alright, so the first thing I'm going to do is to set out my x and y values. I'm going to normalize them. I'm going to call it x equals to MU. Let me use hydro for my x value. Hydro generation actual. To use it for my x. generation actual in NU. In NU. Then I'm going to get the values, right? Values. And do the same for my Y value as energy. The total actual production. The actual production, the values of those. So I'm just extracting the values of those in my X and Y. So the next thing to do is to do normalization of data. I'm going to subtract the values. I'm going to subtract the mean from the values. Then I'm going to divide it by the standard deviation, that is the STD, right? So x norm. Yeah, I'm going to normalize the selected data. Let's normalize this data. It's going to be like x. I'm going to call it x norm. It is x normalized. X underscore norm goes to x minus x dot mean, the mean of x. I'm going to divide up that by the standard deviation of x, divided by student. I'm going to normalize my y as well, my y values. Y norm, norm, that is norm, and norm equals to y minus y mean, divided that by the y standard deviation. Okay, so I'm going to do the after we normalize our data, we are going to fit the polynomial. I'm going to fit the polynomial. But before then, I'm going to I'm going to visualize my x and y to see. I'm going to plot that. Yeah. I'm going to copy this. X and y. Yeah. So what they look like here. So I'm going to do alt.scatter x and y. And y. That means it's not correct. That means I'm using Alright, so this is what my data looks like. So we go back to our code right here, and We know that most data are not in a linear relationship, so we can use polynomial fitting. Polynomial fitting follows it follows same uh, concept of linear fitting, right? It's just that we use a n degree polynomial to describe the relationship of our data. So the curve fit is a good approach as it can be used for fitting all functions, right? And the only code that we are going to change is the code of the functions that I want to fit in our data. So that's the only thing we are just going to change there. So when we are doing fitting, NumPy has a built-in function called numpy.polyfit. That is what we are going to use, numpy.polyfit, right? np.polyfit. So we use x to c equals to np numpy.polyfit. We give our argument. This numpy.polyfit is where the actual fitting happens, right? That's where the actual fitting happens. It's independent variable as our first argument and the dependent variable as the second. So it's going to be x num, comma, y num, the normalized data, right? Comma, what degree? The degree of, since we are doing polynomial, we are going to use, if we use 1, that means we are doing a linear fitting. If we use 2, we are doing a quadratic fitting. But 3, that means I'm doing a polynomial fitting. And I can use that from there. I can say, can impute this in my code like energy, comma, degree, polynomial fitting of degree 3. Degree equals to 3, right? Alright, so yeah, I just have my degree here. Instead of writing 3, I just have my degree. Yeah. Okay, I'm going to call this the coefficient. Let me call this the coefficient because this function gives us the list of coefficients, right? Coefficient. Alright, so coefficient. So we actually know the coefficient of this function here produced here, right? We can do, so I'm just going to do this first. So I don't want to call this function, and I'm going to print coefficient. Yeah, indentation error, of course. Number, sorry. Unsupported open for std, yeah. Every 3 is not defined, so I'm just going to change it to 3. So to explain, I'm going to see just now. Okay, here is the list of coefficients. From the equation a b c d. So here is the list of coefficients, right? There's a list of coefficients that we given. If we change here to S1, that means a linear fitting, you're going to see the coefficient is going to change. So it's just going to give us this and this. And if you change it to 2, that is a quadratic fitting, we're going to have AS, the formula for quadratic ABC, ax squared plus bx plus c. So yeah, we are going to have coefficients right here. Now, but since we are doing a polynomial fit, we're just going to leave it as 3. Then return everything back to normal. I just did that to show the coefficients. If you want to cover the coefficients shown here, we are going to use there is a numpy function called the np dot only 1d. 1d stand for, I'm just going to write that first. I'm going to call it polynomial model. Equals to np dot only 1d. 1d means one dimension, right? One dimension of the coefficients. So that means using this here, using this poly 1d means we want to convert the coefficient into a function, right? Coefficient. Alright, so that's like fitting the polynomial. So we're going to do degree here. There's degree. I'm going to do some polynomial prediction here. Prediction. I call this y polynomial. Call this y polynomial equals to polynomial model. We're going to model it. Polynomial. Polynomial. Model. The coefficient here of what? A function. I'm going to use the x norm for it. Right. So I'm going to sort normalized data. Let's sort it. I'm going to do x sorted. X sorted equals to np.sort. np.sort is the numpy function we use for sorting x norm. And go. So I'm going to I'm going to do y polynomial sorted as well. Polynomial sorted is to polynomial model of x sorted. So this sorted value here, we're going to model it x sorted. Alright, so the next thing is to do, we're going to display our plot. I'm going to do plot the original data. original data, and the fitted curve. And the fitted curve. So we are going to show our plots, and for this I'm going to use a style plt.style use, style use, style, style, style.use. Let me use Cbon. Then my plt.figure, plt.figure. I'm going to use 8 size, 8, yeah, correct. So I'm going to create scattered plots for the normalized data. So I do plt.scatter. Next now, since I'm plotting the line on the original data, label is the actual data. I'm going to call out the actual data. The actual data, I'm going to use a color. I'm going to use green. Then I'm going to use alpha. Alpha is going to use 0.8. Use 0.8. 0.8. Alright, so now I'm going to plot the fitted curve. So this PLT, the fitted curve is going to be a line dot plot and sorted, and the y polynomial, that is the model. Y polynomial sorted, polynomial. This one right here. I'm going to plot the x sorted here against the y polynomial sorted. Since we are doing the prediction, we are going to plot the fitted curve. So polynomial sorted. I'm going to give that label. I'm going to label it as use polynomial fit. Label equals to polynomial fit. I'm going to use the color there. I'm going to use blue. I'm going to use blue. I use a line width. Use a line width. Line width will be use 2 for my line width. Alright, so let's see that x label. The next label is the hydro generation actual. I'm going to use a font size of 14. And for my y label, plt.y label, is the total actual production. going to use a font size there. Size 14 as well. My title, here to the title. Okay, I'm going to use the polynomial fit, right? Polynomial fit. Good. I'm going to set my x ticks and y ticks. Dot x ticks. I'm going to set that this font size using 12. This 12 and legend. To show can open right, right, so we have one error. This one polynomial. Polynomial. So here we go. This is our actual data. The green one is our actual data. While the blue curve that is giving a parabola curve. Yeah. This is a polynomial fit. This is the fitting on the data. Fitted curve. Right. So moving on is we have to do a let me see confidence interval and the error bar. Okay, so to do that, and we are also going to predict some new lines. So to do that, we go back to our code, the confidence interval. So just here, I'm going to do my confidence interval here. I'm going to get the confidence interval and the error bar. Call it error. Then the error bar, you subtract the y node from the y polynomial, the fitted yeah, minus y polynomial, y polynomial. So std error. Let's call this std error because I'm going to get the standard deviation of the error of the std. numpy dot std of the error. So to get the confidence interval, I'll call it a different name. Confidence interval. STDL, same thing, STDL, okay. Okay, STDL. So we are going to make some prediction as well. We are going to make some prediction. But before I get to that, I'm going to plot the confidence interval first to see how it looks. To say to say confidence interval plot, right? Let me just call that confidence interval plot. So to plot the confidence interval plot, you are going to use fill in between. That's PLT dot fill in between. PLT dot fill between between. How do you fill between the normalized uh, the x sorted, the sorted variable of x, that's the x sorted. My polynomial, my polynomial sorted is interval, that is minus the standard deviation of error. Is STDR, right? Yeah, minus confidence interval. Confidence interval. Then the y polynomial sorted plus the confidence interval. Y polynomial. Confidence interval. I'm going to give it the color of red just to see red. Yeah, I feel that makes sense right now. Accepted. Great. And so we have share. Confidence interval is we need to use alpha for that. To use 0.3 confidence interval. Give it a user. Great. Sorry. There you go. This looks better. Alright, so what we are going to do is the error bar. We're going to fill the error bar so and then we're going to predict some lines. So predict some endpoints, right? They are just basic random points. Let's to predict. Let's do to make prediction. We're going to take some points. Take some points, right? Take some points for A, B, and C, which is new points. I'm going to call it point equals to np dot. We're going to put that in an array, right? We're making a point to be an array. And we have this point. Let's do minus 1.5 minus 1.5 1.5 comma 0, for example 0 to 1.5 to 1.5, right? So predicting the point, we're going to predict the point. Predicting the points. It goes like predict. We're going to fit that as well. Let's call that predict, right? That's not polynomial. Polynomial model of the points. And we have an upper bound and lower bound for it. Upper bound. There is a confidence interval. In the lower bound can be subtraction. Right? Just as we have right here, what we did there is what we are just repeating here. We are just giving it a name, upper bound, lower bound. Excuse me. Alright, so what we do next is let's go to the split. So we're going to show the new plot, right? So that'll be I'm going to show it right here. So I'm going to show the new plot, right? So that will be the prediction and error bar. Yeah, I'm going to plot the prediction and error bar. The plot the prediction and error bar. So use scatter for the new points. So you're going to have like 3 points three major points, 1 to 3. Points, points by result, you predict right there. Color, like a color, I'm going to use purple as my color. Purple, then label it. Um, yeah, I'm going to label it like prediction, right? Yeah, label it prediction. I'm going to use it a size. I'm going to use it a size because it's going to be a distinct, their predicted point, so it's going to be distinct. So let's give the size. Let's do s equals to, let's use 200 for that. 200. Then to plot the error bar, use plt.error bar. To plot error bar, use plt.error bar. Of points, now predict. And plotting error bar, you have your evidence interval. So the confidence interval. We need to give that a color. We need to give that a color of give that a color of orange. That's why we have different colors. Orange. And since it's predicted points, I'm going to label it as uncertainty. Uncertainty in quotes. Alright, so let's show that and see what we have. Okay, this is 200. This is 200, no, wrong. Syntax error. Oh, right, there's a command. Syntax error. Type error. It's an array, right? Type an array. How do you imagine an array? Should then brackets. Good. Alright, so this line is the uncertainty line, the orange line. Why this new points there? These three new points, they are predicted points, the prediction right there. Alright, so I think we are done with fitting and prediction. I'm moving to clustering. To clustering. Alright, so the next thing I'm going to do now is to use the able method. I'm going to use the able method to know the number of clusters I'm going to use for my clustering. There are other methods I can use. I can use the select method, but I just want to use the able method. So I'm going to go def plot able method, able method. So create my doc string of the plots the able method to find the optimum number of cluster cluster. So I'm going to prepare my data. I'm going to prepare my data. Prepare the data. I'm going to call that energy cost. I'm going to prepare all my data. Energy cost. As energy. And I'm going to copy. I'm going to use all data. I'm going to normalize my data. I'm going to normalize everything. Normalize data. Scalar. If you remember in part 1, I discussed what standard scalar was. Standard scalar in my life. Fit of scalar. Transform. Going to transform my energy cost. But the next thing is to set within cluster sum of square, that is the W, CSS within cluster sum of square. We're going to set that to 0. Set that to 0. Right, enter. Then we go. What we want to do here is compute. Before then, I'm going to go compute. Just so you understand what we're doing. Compute within cluster sum of square for different cluster size. Cluster size. So go WCSS Set it to okay. Then end range. To find our end range. End range equals to page range from 1 to 11. And for n, then end for any end range. Then to maintain the key means. I also explain what key means does and part one of this video. N plus there, which is equals to n. What we done is equals to n. Now I'm going to set the random state or the initial random state to use text2. It's a random state though, so you can use number text2. I'm going to use text2 for that. So I'm going to fit the normalized data. K-means dot fit. So K-means dot fit normalize. Then I'm going to obtain within cluster sum of square. I'm going to obtain the K-means dot nature. I'm going to show the overplot. Plot the elbow method. Plot the elbow method here. I'm going to use another style, pyt.style. Style that use. I'm going to use here. I'm going to use ggplot. Ggplot and star. To as you show at figure at pixels to use 8,5 or 8,8. I'm using 8,5 here. I'm going to plot parenting of plot the range as the end range within cluster sum of square, and I'm going to use the marker that equals to it. And to label it, I'm going to use the line style. And then I'm going to label my axis t dot x label and y label. X label is the number of clusters. Use the font size for 14. bold it as well. Put that and my while label. Got that my OBD. Because that's one of there. It's also known as the inertia, right? I'm going to call that the inertia as well. Inertia. This one. With the font size. Font size of 14. Going to give it width as well. Width. Use bold. Then the title. Into the title. This is other method. Other method. For base number of constant. Clusters. Font size 14 as well. Double it, here and bullet with little board, here my S6 and Y6 PLT S6 science check then good something for Y until outside good to the middle good. I'm going to display my plot by using PLT but show. I'm going to call my function right there. Before then, I'm going to return right error. Yeah. Okay. And then the clust is not defined. Image clust should be defined now, right? Let's see. In cluster. Oh, type error. Let's see where that is. Stars. In a moment, it's going to show our elbow plot. If everything works fine. No. Well, it works fine. Yeah, these are available property as weight. Well, weight attribute error. Weight. It's just some crazy shit out there. Everything should be fine now. Yeah, perfect. So here is our elbow method. When we are looking at this, how do we know the number of clusters to use in our elbow plot? Well, we can see from the plots that as the number of within cluster sum of square decreases, then the number of clusters increases. So the best number of clusters is always chosen at the elbow point where any further increase of clusters do not have any major decrease on the WCSS, right? Right, so here, which number? I think is 4. At point 4, the increase of the number of clusters does not have any major decrease on the WCSS, right? Yes. So the point 4 is the optimal number of clusters. That's the best number of clusters you are going to use. Point 4. Yeah, 4. Alright, so then we could proceed to our clustering. K-means clustering. So do def this plot. Okay, that's a scatter. Clustering. I'm going to use, like I said earlier, when we are doing clustering, correlated data does not work well when you are performing clustering on your data, right? So we are going to check its map to know which data are correlated or not. So from there, we'll know the data we are going to use for our clustering. So we are looking for not correlated data, nuclear generation estimated, and thermal generation estimated for my clustering. Yeah, so energy to cost. the nuclear. I'm going to use this nuclear platform. And I'm using the thermal generation estimate as well. Generation estimates. I'm going to copy that as my new. Let's copy that to energy to plots so it stays in there. It goes to standard scalar. Then my scaled energy. And that fits transform the energy to plots. Alright, so I'm going to fit the K-means model right now. Fit the K-means model. Next thing is to fit the K-means model. Fit. K-means. Still K-means. The number of clusters, that is the n clusters, which we are going to, which is going to be 4 from here. We're going to use 4 as our number of clusters. So 4 in the random state. State. Use state 2 as well. Use state 2. So energy lost. I'm going to call this energy cluster. Because I'm making another table. I'm making another column in my data set. And I'm going to call that cluster. Also K-means dot fit predict. Yeah, fit predict, right? Is it? Yeah, predict. This scaled energy. Scaled energy. And let's plot now. Need to use blt.style. Use. Need to use ggplot as well. Ggplot. Big size. Interesting. Nothing. Then I'm going to create a scatter for the. I'm going to create a scatter for the cluster. Space. call that scatter, right? So I can call it scatter. Choose scatter. BLT scatter of what? Of the scaled energy. Zero. And I'm going to call it C is my energy. Energy linear table. Energy constants. Constant. I'm going to use a C map here. And I'm going to call it I'm going to use radius of I'm going to use of 0.9. I'm going to label it as my data. So the next thing is to plot my k-means with cluster centers. I'll be PLT dot scatter cluster center from 0 to 0. Cluster centers from 1. I'm going to give that a size of 100. Size of 100, let's see. S. Let's give that size of 100. Let's use to mark it. I want to mark it as P. Use P elevate as well. Cluster center. Elevate as cluster center. Right. So I have my C bar, my color bar, my C bar as BLT dot color bar. BLT dot color bar. Color bar scatter. Color bar scatter. I'm going to set it. Set the ball. And that's add cluster. Font size. 14. I'm going to use 14. My title and others. To the title here. I'll be k-means Taking the mode plus 3 reinforcement of 4 number of clusters. And to give the font size, to give that font size of 16. Yeah, I think that's label, X label and Y label. I'm going to give a font size of 14, 12. So font size of 14 or 12. I'm going to give it 14. Then my Y label. Only the comma. I'm going to give that font size as well. Font size of 14. Size of 14. Yeah, my headers and legend, my stitch and my teach. BLT stitch. I'm going to give my font size of 14. Font size of 14. And my BLT.y teach. And the font size of 14 as well. Legend. My legend. BLT.legend. You want to locate it in the best position. The best position on the front side. On the front side of 12 or 14. Just 14. Yeah. LT.show. Show it and return. Yeah, so I'm going to call my function. Invalid syntax. Syntax error. Name error. Do we have that? Looks fine to me. Oh, right. Let's see. And close stars. And close stars. color bar, color bar. Yeah, there we go. So this data, these are data, and the one in black is our cluster center. So notice that we use the normal clusters, it's four. So we have one, two, three, four, right? These are green because they are close to this point. So they are green. Assuming these points are somewhere here, then probably might have yellow as their color, right? Because they are closer to the yellow point, to the cluster, to the center here. Alright. So this green here, I'm seeing a lot of things here. So this green here seems to be closer to this point, to this center, than this center. The distance between this point and this center is closer compared to from this center to this point. Right, so and the last thing we are going to do here is to make some predictions. Alright, to make some predictions, I'm not going to do it on this. I'm going to do it separately. I'm just going to do some same code. I'm going to just copy the code. I'm going to copy the code and then add my predictions to it. New cell, clustering prediction, clustering prediction. So what you're doing here is to predict. You're going to predict points and question says prediction points. Show the clusters. Okay, so we prepared our data for clustering. We fit the k-means model. So now we are going to, from here, we are going to predict our new points. Yes, predict new points for clustering. I'm going to pick some points, random points, So let's call it points. This is an array of points. Array of points. Let's go. Here's minus. Let's start from minus 25, minus 2.5, and minus 2.0. Let's produce another point. call that I'm going to use random points. So I'm just going to use 25 on the x-axis and we'll pick 950. See what's happening on the y-axis. Do one more point. I'm going to go 3.1, 3.1, let's say 3.1 minus 0.5 on the y-axis, 0.1. So I'm going to scale these new points here. I'm going to scale them. Once I've scaled uh, the initial points, data points here, I'm going to scale them as well. Scale. Scale new points. Now the scaled point. Scalar dot underscore point underscore sorry point cluster predicted stop predicted also training. I'm going to the next thing is to visualize. I'm going to visualize the predicted cluster. And original clusters. Original clusters. Built figure. Okay, so we are going to do that here. I'm going to plot the new ones here. Plot the predicted quantity. Plot the predicted points here. So here I'm going to use for loop. Get it for start in wait. Then I'm going to zip it. I'm going to zip scale points. Close down. Predicted. Pivot to the scatter. Pivot to the scatter. New points. Points. The x and y. New points. This one. I'm going to use the color blue. Color is blue. color is blue, I'm going to use, should I use edge color? Okay, the color is brown. I want to size it, so just now since I have the new points, to size it as 100 as my point. And I'm going to label it as label do F. Plus 1 dot test, new points, zero point 1 format. Format here, format is format P points. Points will be iteration. Color is, yeah, since I'm using iteration, I'll stop right there. Alright, since this should be title, Kevin cluster 4 number of clusters, and my predicted point now, and predicted point. So let's see. Combine function. Then brown is not defined. Brown is not defined. X does not have value iteration names, but standard scalar as fitted with iteration names. I'm just going to ignore this. Alright, so here are my new points. So I'm trying to cluster 1. So new point 1, so cluster 1. Here are my new points, which is point 1, point 2, and point 3. It's not attaching them to the main cluster, so something is probably wrong. This is point 1 to cluster 1, point 2 to cluster 2, which is not even close to cluster 2, point 3 to cluster 3. Oh, there it is. Two clusters, attach them to the clusters. Cluster. Yeah, looks fine now. This looks better. So this point 1 is closer to cluster 2, and point 3 is closer to cluster 2 as well. That means this is cluster 2, while point 2 is closer to cluster 1. This is closer to this. These two are closer to this. Right, so let's say we have another point. 50 and 1000. Let's see where it's going to attach in the cluster. Right. So we have got points and it's closer to cluster 3. So this is our cluster point 1 and 3 are closer to cluster 2. This is cluster 2. The green one is cluster 2. This is cluster 2. Point 2 is closer to cluster 1. Point 4 is closer to cluster 3. One, 2, 3 is closer to this. Right. Right, so there we have it, the completion of my assignment. I have my chemical stream and my prediction here, my elbow method, my polynomial fit and prediction, and scatter now my map, scatter plot, histogram, and bar chart. Right. I'll see you guys in the next one. Please click on follow button. Please like and subscribe to my channel. Bye guys. See you on the next one.